Today we're going to look at section 3.4, which covers perpendicular lines. And the learning goal that I have for you guys is that students will prove and apply theorems about perpendicular lines. So let's start by talking about this word perpendicular bisector. You already know that two lines are perpendicular to each other if they meet at a 90-degree angle. That's one thing we have already talked about. But we say that something is the perpendicular bisector if it bisects a segment and is perpendicular to the segment. So it must go through the segment's midpoint and it must form a 90-degree angle. Okay, so if we look at this picture right here, we can see there's just a teeny tiny little piece of information that's missing. We can see that these two segments are congruent to one another, but we don't yet know that the segment is perpendicular. So if I draw in that little 90-degree angle, now I have everything I need. And what I would say is that ray, RT, is the perpendicular bisector of segment AB. And you can even use your symbol, so perpendicular bisector of AB, segment AB. Boom, just like that, okay? So it cuts it in half and it meets at 90 degrees. So let's practice drawing a couple things. Let's draw the diagram. RT is the perpendicular bisector of PQ, but PQ is not the perpendicular bisector of RT. So let's start by drawing RT. In fact, let's not even draw it perfectly straight, because not everything is always perfectly straight. So here's RT. It's the perpendicular bisector of PQ. That means PQ is actually the one that's getting cut in half. But PQ does not bisect RT, so that means RT does not get cut in half. So perhaps PQ lives somewhere like right here. And let's talk about what's going on here. So here's P, here's Q. If RT is the perpendicular bisector of PQ, that means these two segments have to be congruent, and this has to be 90 degrees. PQ is not the perpendicular bisector of RT, which means RT does not get cut in half. The two lines are still perpendicular, but these two segments here and here are not going to be congruent. Let's do another one. Let's draw the diagram where GH and KL are perpendicular bisectors of each other. So again, let's start by drawing GH. Any old segment in here. Here's G, here's H. So if the two segments are perpendicular bisectors of each other, they're both going to cut each other exactly in half, and they're going to meet at 90 degrees. So we'll put K up here and L up here. So I need to show that these two segments here are congruent and these two segments here are congruent, and I've got to show that this is a 90-degree angle. One word of caution in this picture, it doesn't say that GH and KL are congruent to each other, so they don't necessarily have to be the same size, which is why I drew KL slightly shorter than GH. I don't really know which one's bigger and shorter, but they're probably not exactly the same length. Okay, so the next thing we should talk about is the distance from a point to the line. And it turns out that the shortest segment, or the shortest distance from a point to a line, is that perpendicular distance. So this is actually how we define distance from a point to the line. It's the length of the perpendicular segment from that point to the line. Let's look at a picture to help understand that. So here if we have a line and a point that's somewhere else that's not on the line, the shortest distance from this point to this line is not going to go straight down like this. No, it's not going to do that. That's actually not the shortest distance. The shortest distance is going to go like this, where this segment is perpendicular to the line. So if that's perpendicular, it's going to be the shortest distance. Okay. Now let's apply that reasoning to some problems. So let's look at this picture here. We have triangle ABC and we have this segment AP. Let's name the shortest segment that goes from point A to line BC. Well, I can see A is here. I can see AP is perpendicular to BC. So we would write AP is perpendicular to BC. So that means that the shortest distance must be AP. Notice when I write AP, I'm not writing the segment sign on top of it. I'm talking about the length of AP. The second part's a little different. This asks me to write and solve an inequality for x. Since I know that AP is the shortest distance, what I can say is that segment AP is going to be less than any other segment where A goes to line BC. So I know that segment AP, for example, must be less than segment AC. AC has to be longer if AP is the shortest distance. So let's fill in the values that we have for those segments. The length of segment AP is 12. That must be less than the length of segment AC, which is x minus 8. And what we have here is a nice inequality, which I can solve. I could add 8 to both sides. And doing so gives me 20 is less than x, or a lot of times we like to write the x on the left. X is greater than 20. Perfect. Okay, so next we're going to talk about a couple theorems that have to do with perpendicular lines, and let's go through them one by one. The first one we'll just call 3-4-1, 3-4-1, and it says, if two intersecting lines form a linear pair of congruent angles, then the two lines are perpendicular. So let's look at the diagram here. So we have two intersecting lines, and here's line L. The other line, M, intersects it in such a way that, yes, it forms a linear pair. Right here we've got that linear pair of angles. But not only do we have a linear pair, the diagram is telling me that those two angles have to be congruent. Well, if we have two congruent angles, let's say that they were both x. Well, if x plus x has to add up to 180, they're both the same, that's why they're both x. Let's solve this equation. If 2x equals 180, divide both sides by 2, we get x equals 90. So if these two angles are congruent, they must both be 90 degrees, and if they're both 90 degrees, then that means that the lines have to be perpendicular. Or in other words, that line L is perpendicular to line M. So let's review what we talked about. If we have two intersecting lines so that they form a linear pair, and we know that two of the angles in the linear pair are congruent, then we know that the lines must be perpendicular. All right, let's look at the next theorem here. The next theorem is important. It's called the perpendicular transversal theorem. You'll use this in your homework tonight. So it says, in a plane, if a transversal, remember a transversal is the line that intersects two other lines. In this picture, it's Q. In a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So if I know that line Q is perpendicular to line N, then I know that line Q has to be perpendicular to line P. We write that in an if-then statement. If N is parallel to P and Q is perpendicular to N, then I know Q is perpendicular to P. Okay, the third theorem that we're going to go over is if 2 is 3-4-3, sorry, and it says if two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. So it's kind of like have like different if information. So what I'm saying is if I know that T is perpendicular to S in this diagram, and I know that T is perpendicular to R, then I know that R has to be parallel to S. So let's write that out in notation. So if I know that T is perpendicular to S, and I know that T is perpendicular to R, then I know R is parallel to S. And really, this is just a special case of the converse of the corresponding angles theorem. If you look at the diagram here, you can see that these two 90-degree angles are corresponding. It forms the F here. So my two angles are corresponding. If corresponding angles are congruent, then my lines are parallel. So it's just a special case of that, where my lines happen to be perpendicular, and so my corresponding angles happen to be right angles. Alright, so one last thing here. We're going to complete a proof. And I know my diagram looks a little complex, but make sure you're drawing it correctly. So I want you to draw it so that EH and FG appear parallel, but we don't know that they are yet. And HG intersects them, so this is a 90-degree angle. Then we're going to put another two transversals in here. One of them is going to go from F down to H, kind of making a little right triangle we see here. Then the other one goes through F kind of at an angle. So we kind of create this like four-sided figure there with the lines. So given, we know that angle EFH is congruent to angle HFG. So EFH, that's this angle that's marked right here, is congruent to HFG. So we know those two are congruent. And we know that FG is perpendicular to GH. So FG is perpendicular to GH. Whew, this looks complicated. We want to show that EH is perpendicular to GH. EH here is perpendicular to GH. So we're trying to show that this is perpendicular there. Alright, so let's begin. Let's start with the first statement that's given. Let's start with angle EHF. EHF is congruent to angle HFG, and that is given, of course. But let's investigate this. If I know that these two angles are congruent, what else can I conclude? Well, tracing these angles, I can see that they form a Z, which means that they're alternate interior angles. Well, I know if alternate interior angles are congruent, then my lines are parallel. So these two lines here must be parallel. So that's my next statement. So I'm going to write, okay, I know now that EH is parallel to FG. How did I know that? I knew that from the converse of the alternate interior angles theorem. Beautiful. Alright, so now that I know those lines are parallel, let's get this other piece of given information into my proof. I know that, FG, not GF, just the way it's written, doesn't really matter, I guess. FG is perpendicular to GH, and that's given. Now that I know that, let's review some of the information we know. We know these lines are parallel. We know this line is perpendicular. So I can use one of the theorems we just talked about. Let's review. Let's look back here. What about this perpendicular transversal theorem? If I know my lines are parallel, and I know two of my lines are perpendicular, then I know my other two lines are perpendicular. So remember in this picture, we said, okay, N was parallel to P, and I knew that Q was perpendicular to N, so I made the conclusion that Q also has to be perpendicular to P. Well, that's exactly what we have going on here. We know that HE or EH and FG are parallel. We know that FG is perpendicular to HG, so we know that's a right angle. Therefore, we can conclude that this is also a right angle, which makes EH perpendicular to GH. So that's my last statement. EH is perpendicular to GH. And the reason is my perpendicular transversal theorem. All right, and we got it. So you'll have like a couple of proofs to try to fill in the blanks tonight, and then some inequality practice, and then trying to figure out again which lines are parallel based off of your given information.